Hello everyone, welcome back for another lesson. In this lesson, we will talk about static electricity, as you can see on your screen. So what is static electricity? It describes the phenomena related to electric charges at rest. That's why we say it's static. Static meaning not moving. So electrically charged objects do not remain permanently charged. In other words, they will exchange charges until both objects are neutral, or at least one of them is neutral. So they'll try to equalize their charges as best they can, but they don't always stay charged. They can lose their charge to water molecules. That's more of a fun fact that I included because it happens often when air is really dry, particularly with girls with very fine hair. Hair will tend to go up, as you see over here. This is obviously an extreme case, but hair can separate like this or like this if the hair carries particles, electrons. So the electrons are repelling each other, and if each little hair is carrying electrons, well, all the little hair are repelling each other, and you get a look like this. So what can you do? You can just wet your hands. I wish I had known this during my teenage years. You just get your hands a little bit damp, and you just pass your hands on your hair, and voila, there's no more static electricity. So in the middle of the winter, if your hair is really dry and it's starting to fly a little bit like this, just get your little fingers a little bit damp and pass them through your hair, and your problem is going to be solved. Now it also says charged objects may get neutral, again, by getting close to another charged object of opposite charge. So we know that the rule with charges says that opposites will attract. So you need to have a positive body and a negative body in order to neutralize those charges. And at that point, if they're close enough, you're going to have an electrostatic discharge. In other words, like a shock. If you rub your feet on a carpet, you are charging your body and your clothes with electrons, with electricity. And as you get closer to a doorknob, for example, if your hand is close enough, that excess of electrons will jump from your hand to the doorknob, which is metallic. We know that metals conduct electricity. So those extra electrons are going to jump to the doorknob and basically travel back down to the floor where they came from. So everything gets equalized and neutral again. Okay, so the objects don't have to necessarily touch, but they have to be close enough for the electrons to jump from one body to the other. So one way to charge an object is by friction. I just talked about rubbing your feet on the ground, your socks, and charging your body and your clothes. So let's take a closer look at how this works. So basically we're creating an imbalance of electrons between two objects. So first I have two objects here. They're both neutral. So they have as many positive charges as negative charges. Both of them do. If I bring them together and I rub them together, so there has to be friction between the two, some of the electrons will travel from one object to the other. And on the next slide, I'll show you how do we determine which object will gain electrons and which one will lose electrons. So there's a way to figure that out. I'll show you after. So some of the electrons will go from one object to the other. Now, if we separate those two objects at that point, we have an imbalance. The one that lost the electrons is now positively charged. It has a deficit of electrons. It doesn't have enough to counterbalance the positive charges, the protons that are within the object. And the one that gained the electrons also has an imbalance, but this one has a surplus of electrons. So because it has more electrons than protons, well, then that one is deemed negatively charged. Now, what would happen if you bring them closer? Not close enough to touch, just close enough so there is an interaction. There would be an attraction because one is positively charged, the other one is negatively charged, and we know that opposites attract. So they would attract each other. If they get close enough or if they touch again, then the electrons will travel back from the surplus side to the deficit side until both sides are equal again and neutral. Okay, so charges would travel until we get two neutral substances again. So that's how we charge by friction, or also how we make things neutral again after the fact. So that is one way to create static electricity. We'll talk about other ways in a moment. So I was saying before, we can determine which substance would gain electrons, which substance would lose electrons. So if, for example, I look at this chart, which is called the electrostatic series. So what this chart says basically is that some substances will tend to gain more electrons and some will tend to give them up. So here it says more likely to become negatively charged, okay? And they have a strong hold on electrons. So they are holding on to their electrons very tightly. They will not give them up, but on top of it, they like electrons, so they'll tend to gain electrons. So at the top here, they tend to get more negative when they are rubbed with something that is lower on the list. So these will tend to, are less likely to become negatively charged. They'll lose their electrons more easily because they have a weaker hold on electrons. Okay, so these, let's say I say glass gets rubbed with, I don't know, piece of rubber. Well, the piece of rubber would be negative and the glass would tend to become positive. Okay, if I did if I went through another example and we said we're going to use silk and we're going to rub it with, I don't know, a piece of copper. Well, copper being closer to the top, copper would be negatively charged and silk would be positively charged after the fact. Obviously, if you bring them closer, because they are of opposite signs, they would attract. If they touched, then the surplus of electrons would go back to the piece of silk until they're both neutral again. But originally, when you first create a friction between the two, this one would become positive, this one would become negative. So that's what the electrostatic series shows you. It's which substance tends to gain electrons, which substance tends to lose electrons, and therefore which one will become positive, which one will become negatively charged after the fact. Okay, so two other ways that we can charge objects. So we just saw friction. Another one is by conduction. So conduction implies that there is a contact between the two objects. Let me show you how this works. So I have here an object that is positively charged. If I bring a negatively charged rod, an object that is negatively charged, and I make them touch, okay, so the rod touches the other object, what would happen? Well, the excess of electrons, some of the electrons would be moving over, and then I remove the rod. Well, this is still negatively charged, but now my object here is also negatively charged. I could have put the positive signs. I didn't want to add them to not confuse you with the example, so I'm just working with the electrons here. But all that to say, originally this was neutral. After I bring a negatively charged object close enough to actually touch it, some of the excess electrons here will move towards my sphere over here. And after I remove the rod, some of the electrons will remain, so it makes my sphere negatively charged. So now I've just charged my object by conduction, so by touching it. Another way would be through induction and polarization. They come together. I'm going to explain to you why. So induction means that I'm bringing an object closer, but I'm not actually making them touch. Okay, so I'm just going to bring it closer. So let's say I bring my rod close enough that there is an interaction without really them touching. So my electrons cannot jump over necessarily. What would happen? Well, we know that electrons repel each other. So this being very negatively charged, these electrons here would say, yikes, let me go away. So the electrons would move over to the opposite side as much as they can. They want to move away from the negative rod. The protons are not moving. They're stuck in their atoms. Okay, so the protons never move. So what do I have here? Well, I have a sphere that is now kind of positively charged on this side, but is more negative on this side. So what happens is by bringing this rod over, which we call induction, we cause polarization. So I've created a positive side, so a positive pole, and a negative side or a negative pole. Okay, so my electrons got repelled, they moved over as much as they could to the other side to move away from this rod. And because of that, the protons stayed where they were, but now this area over here is much more positive than before, and this area is much more negative than before. So I've really created two halves, in a sense, within my sphere. Okay, so this is what we call polarization. So induction, because I'm bringing an object with a charge closer, but it forces the electrons to move away and it creates poles, a positive and a negative pole, which we call polarization. So the induction part, the bringing the object closer, caused the polarization, which is causing the movement of electrons away from my negative rod. So they go together. Now, what would happen if I move my rod away? Well, these electrons are presently repelling each other, but there's nothing in their way anymore. So they will move back to where they belong and away from one another to kind of create a neutral sphere. Okay, so that's induction, which causes polarization. So these are the three ways to create a charge using static electricity. So there's friction, there is induction and polarization, and there is conduction. So yes, there is a movement of electrons throughout the process, but at some point the electrons stop moving. They're not constantly moving. So that is very different than what we call dynamic electricity, which is basically the electricity that comes out of the wall and powers the fridge and the charger for your phone and the TV and whatnot. Okay, so these charges are at rest most of the time. That's why we call them static. Now, when we talk about charges, we talk about size of charges and how strong their interaction is. So we call that a force. We know that all forces are measured in Newton. Now, Mr. Coulomb, if you recall, Mr. Coulomb is the one that said that there's a certain amount of charges in, because charges are very small, we're going to group them together in a certain group, and we're going to call that group of charges Coulomb. Now, Mr. Coulomb came up with an equation to measure or to calculate the force between those charges. And this is what the equation looks like. So the force between two bodies that carry a charge, measured in newtons, is equal to a certain constant. You have the value over here, 9 times 10 to the 9 Newton per meter square over Coulomb square. Very complex. Remember, it's 9 times 10 to the 9. That's the important part. Times the object number 1, its charge. So Q1 is the charge of the first object measured in Coulomb. Q2 is the charge of the second object measured in Coulomb over our, this should be squared. I don't know why it's underscore. So it should be squared. Let me correct that. Okay, so it should be over r squared. R represents distance. So I don't know why they put R. I prefer D. So I've rewritten it. I like to use this version also. It's not, although it's not the official one. I like to use this version. So there are two differences. I put D squared for distance. And also I've made the fraction the entire length of the equation because we know that to multiply and then divide only this part comes out to the same as dividing by everything. Multiplication, division are kind of, equal in terms of types of math operations. So this, I think, is the simpler version that you might want to use. But this is the official one, okay? So K is 9 times 10 to the 9. Q1 and Q2 are the charges for the two charge bodies measured in Coulomb. And this is the distance squared. And this is a physics equation. So distance, again, is measured in meters as usual. We have calculate the magnitude of the electrical force if the charge of the first substance is 6 times 10 to the negative 10 Coulomb, and the charge of the second substance is 4 times 10 to the negative 8 Coulomb. The substances are placed 2.5 centimeters apart. So let's see what we would do with that. Okay, so we have, so they want us to calculate the force. So F is equal to 9 times 10 to the 9 is the constant, times Q1. Q1 is 6 times 10 to the negative 10. I will put this in brackets just because there's a lot of times. Times the second charge, so this will make it clearer, in other words. 4 times 10 to the negative 8 Coulomb. This is in Coulomb. I will spare you the units for this. And divided by the distance squared. Now remember, this is in cm, but it has to be in meters. So I would have 2.5 cm divided by, there's 100 cm in 1 meter, and I have to square this. Okay, so this I have to convert into meters and then square it. And that would give me 3.46 times 10 to the negative 4 newtons. Okay, so it's just really, as I would call it, plug and play. You put in the numbers and you solve. Okay, next we have, what is the distance between two particles? Let me just grab my pen again. Between two particles when the first, with a charge of 6 times 10 to the negative 6 Coulomb, exerts an electrical force of 0.312 Newton on the second, which has a charge of 8 times 10 to the negative 8 Coulomb. Okay, so I have the force, 0.312 Newton is equal to 9 times 10 to the 9, as usual, times my first charge is 6 times 10 to the negative 6 Coulomb. And my second one is 8 times 10 to the negative 8 Coulomb. And they want to know, what is the distance between the two? Now don't forget, this is squared. So once you start rearranging things, what are you going to have to do? So if I rearrange, I would bring this over. Okay, now I should be able to move it. So this is going to go underneath here, right? If I rearrange my equation, and my d is going to go over here. Okay, so originally what I had was this, because I don't want to confuse you. So this is what I had originally. Now, if I rearrange mathematically, I will send this over here and this over here. But let's not forget, this is squared. So if I want to get rid of my square, because I just want the distance itself, I need to square root both sides, right? This should go all the way down here. So I should calculate all this, square root it, and that will give me basically the distance itself. And so your answer should be 0.118 meters. Lastly, Amanda has rubbed a balloon with wool to give it a charge of -1 times 10 to the negative 6 Coulomb. She then acquires a plastic golf club carrying plus 2.5 times 10 to the 13 elementary charges. She holds a plastic golf club at a distance of 50 cm above the balloon. Determine the electrical force between the golf club and the balloon, and are these objects attracted or repelled? So let's take a look at the second part. Are they attracted or repelled? Well, the first one is the first one is negatively charged. The second one is positively charged. So because they are of opposite charges, they will be attracted. So that's the easy part. Now let's look at the math. So if we look at the math, we have to determine the force. So the force is equal to 9 times 10 to the 9 times the first charge, which is, and we'll just use the absolute value, 1 times 10 to the negative 6 Coulomb. But the second charge, it says elementary charges. And so that means these are individual electrons or protons, sorry, in this case, because it's positively charged. So what do we need to do? We need to take the 2.5 times 10 to the 13, and you might want to do this in a separate calculation. And we need to divide this by the number of charges in 1 Coulomb. If you recall, what it is 6.25 times 10 to the 18 protons in this case, okay? So that will give us the number of Coulomb that this actually represents. Then we take that divided by the distance squared. So the distance is 50 cm, so we need 50.0 divided by 100 cm to get this in meters. And we need to square this. So the answer should be, they are attracted by a force of 0.114 newtons. All right, I hope this was clear. If you have questions, don't hesitate to reach out. And otherwise, I'll see you around for your next lesson. And until then, take care.